So we're continuing to look at the chain rule and looking at more examples. I just threw up the chain rule again in front of you so you could recall. So I'm just going to look at if we have a composition of two functions, f of g of x. So we can write that as f parentheses g of x is differentiable at x. Then the derivative of that composition function is the derivative of our outer function, keeping our inner function the same, times the derivative of the inner function. Or if we wanted to, we could go through and we could figure out what is that inner function. We're going to choose that to be u equals g of x. And then we can let y equals f of u, and that would be our composition of f of g of x. If we want to look at it this way, then we can say, well, the derivative of y with respect to x, this is equal to looking at the y function in terms of u and taking the derivative of y with respect to u, and looking at our function u with respect to x, so taking the derivative of u with respect to x and multiplying those together, where dy du is evaluated at u equals gx. The other one we looked at was the derivative of e to the u, where u is some function of x. If we take the derivative of e to the u, basically that's just itself e to the u times the derivative of the exponent. So another way we could have written that is if y was equal to e raised to the f of x power, some function, then the derivative y prime, or another way to write that is dy dx. Or another way to write that, just so we get used to this, is d dx of our function e to the f of x, because we haven't taken it yet. This is equal to the original function itself, e, times the derivative of our exponent. So f prime, I usually put that in front, the derivative of my exponent, times e to the f of x. So just a reminder of those derivatives. Now looking at our derivative in front of us, our example, we have y is equal to 2x minus 1. That quantity is raised to the negative 1 power, and then we have x squared minus 5x, and that quantity is raised to the 6th power. So when you're looking at these, you should think to yourself, what type of rules am I going to use? Well, how it's written right now, notice we have a product. You can think of this as a product of two separate functions. And I notice that when we take the derivative of the first function, I need to use the chain rule. And when I take the derivative of the second function, I'm going to need to use the chain rule. And so we're going to first need to use the product rule. So dy dx is equal to, so I'm just going to write down the product rule, and then we're not going to do this very much longer. So we're going to take the derivative of the first, 2x minus 1, raised to the negative 1 power, times the second, which was x squared minus 5x raised to the 6, plus the first. So the first in our case function is 2x minus 1 raised to the negative 1 power, times the derivative of the second. So d dx of the second, x squared minus 5x raised to the 6. Okay, so now when we take the derivative of that first function, we need to use the chain rule. So we want to bring our exponent down front using the general power rule here. So negative 1 times what's inside, 2x minus 1, and subtract 1 from our exponent. So subtracting 1 from our exponent of negative 1, we can pull, we get negative 2. All times the second function, x squared minus 5x to the 6, plus the first function, leave it alone, 2x minus 1 raised to the negative 1.
Wait, doesn't the derivative of 2x minus 1
Yes.
need to?
So correct. So thank you. And it's easy to forget, guys. So the derivative, chain rule, derivative of the inside. So derivative of 2x minus 1, that's just going to be times 2x right here. Thank you. And so derivative of the second function, chain rule again, bring our power down, 6x squared minus 5x. Subtract 1 from my exponent, I get 5 times the derivative of the inside. So derivative of x squared is 2x. The derivative of negative 5x is minus 5.
2x minus 1 just be 2, not 2x.
Thank you. Thank you guys. So this should have been just 2. Okay, I'm glad that you guys are standing right next to me and watching. Thank you. So we need, we're not done, and we can clean this up a lot. And so you're going to have some problems on your homework where you're going to need to notice that we can factor some stuff out here. And so first of all, let's just look at this x squared minus 5x raised to the 6th power, and I have an x squared minus 5x raised to the 5th power. So we have 5 of those in common. So we can pull out this one of these x squared minus, actually not one of them. We're going to pull out 5 of them, x squared minus 5x to the 5th. I'm just going to look at my coefficients really quickly. So I have a coefficient of -2 for this first one that's outside of the parentheses. And my coefficient for that second grouping, I have this 6. So I'm looking at what those two have in common, 6 and 2. I can pull out a 2. We'll do that there. These have negative exponents. Let's pull out the smallest one. So the smallest one here, right, is 2x minus 1 to the -2 power. -2 power, -2 is smaller than -1. So let's pull out this 2x minus 1 to the -2 power also. Okay, so let's see what we have left when we pulled out a 2. So that goes away. We pulled out 5 of the x squared minus 5x to the 6. So we're left with one of them left. So we're left with an x squared minus 5x. We have this negative out front. And then we pulled out all of these, 2x minus 1 to the -2 power. So that's all that we're left when factoring that out of the first grouping. Plus, okay, so thinking about, we pulled out 2 from 6. So we're left with a 3. We pulled out all of the x squared minus 5x to the 5th. We're left with this 2x minus 5. I kind of waited, but let's figure out what we have left here. So remember, power to power is, sorry, not power to power. When we have the same base and we're multiplying, we add our exponents. So kind of thinking backwards, what would I add to -2 to get back a -1? Well, I would add 1 to -2 to get back -1. So I'm left with one of these in here when I factored out a -2. So 2x minus 1. So I'm going to clean it up a little bit. So I have 2, we have x squared minus 5x to the 5th, 2x minus 1 to the -2. Let's distribute this negative sign inside my parentheses here. So I got -x squared minus, actually plus 5x plus 3. And then we can distribute. I'm going to distribute out these 2 parentheses before I distribute my 3. So I have a 2x times a 2x is 4x squared. A 2x times a -1, so that's -2x. -5 times 2x, so minus 10x. And -5 times -1 is +5. So 2 times x squared minus 5x raised to the 5th. All times 2x minus 1 raised to the -2. Let me just put this underneath to save some time. If we factored or we distribute a 3 here, 3 times 4x squared, that's 12x squared. And we have a -2x minus a 10x, so that's -12 times this 3 out front. That's -36x. And then we have a 3 times that 5, so +15. So if we combine like terms inside this bracket, I have a -x squared plus a 12x squared. That's going to give me plus 11x squared. I have a 5x minus 36x. So that's a minus 31x. And then I have my plus 15. And so we found the derivative of our function, which is this. So we could have started by writing that differently and then taking the derivative. So I notice also, noticing our original problem, notice we have that 2x minus 1 to the -1 power. We could have rewritten that with a positive exponent. And we could have said this is the same thing as y equals x squared minus 5x to the 6 all over 2x minus 1 raised to the first power, making that exponent positive. And then go about taking the derivative of that with using the quotient rule. And within the quotient rule, when we take the derivative of the numerator, we use the chain rule. Okay, so some of your problems, again, on the homework, you're going to have to notice that you can factor out some of those parentheses and simplify it that way. It's helping us now doing all that kind of algebra because we're going to have to be, or we're going to be looking at when are these derivatives equal to 0 and finding out when is our derivative negative and positive. And so setting this ugly function, this derivative equal to 0 is easier to do when it's all factored. And then we can just set each factor equal to 0 and solve. Let me pull another problem up. Okay, so looking at the following, we have y equals x squared times secant of 1 over x. And again, we want to find the derivative. So we want to find y prime. So again, looking at this, I would notice that I need to use the product rule. Before I do this, I really don't want to, when I take the derivative of the inside of secant x, secant of 1 over x, I don't want to have to use the quotient rule on 1 over x. And remember, we can rewrite things. So let's rewrite that as x to the -1 power. And so doing that, we have y is equal to x squared times secant of x raised to the -1 power. So that's different than saying the inverse function of secant of x. Okay, so now we can use the product rule. So the derivative of our first, not bad, right? 2x times the second, secant of x to the -1 power, plus the first, x squared, times the derivative of secant x to the -1 power. So my outer function is secant. So I need to remember what the derivative of secant is. Well, that one didn't start with co, so we know it's positive. And secant, that one is secant tan. So it's secant of the original inside function, which is x to the -1. Oops. Times tangent of our inside function, which is x to the negative 1, times the derivative of our inside function. So the derivative of this inside function, x to the negative 1, using the general power rule, if we bring down negative 1 and subtract 1 from our exponent, we get negative 1 x to the negative 2 power. So y prime equals 2x. I'm just going to rewrite it just because our original had secant to the 1 over x, secant of 1 over x plus, so actually, notice right here, we have this x squared times this negative x to the negative 2 power. So that's going to give me a minus in front. But if I take x squared times x to the negative 2 power and I add my exponents, 2 minus 2 is 0. So that really gives me x to the 0 power, right? Which is just 1. Times, well, secant, we can rewrite x to the negative 1. So secant of 1 over x, tangent of 1 over x. So let's factor, let's pull out what they have in common, and notice each factor, they have a secant 1 over x in common. So we can pull out that secant 1 over x from each piece. So if we pull that out of here, then we're just left with 2x. If we pull the secant 1 over x out of the second piece, we're left with minus 1 times tangent 1 over x. So minus tangent 1 over x. Okay, so we found the derivative of y.
So does the negative 1 times x to the negative 2 squared, does that cancel out with the x squared over there?
Yeah, because it's not that it's subtracting, it's just that we're multiplying. So if we multiply x squared, don't like that big one. So x squared times a negative x to the negative 2, I could pull the negative out front. And then because they're the same bases of x, we're adding our exponent, so plus a negative 2. So that gives us to the 0 power, which is just negative 1.
Gotcha.
Other questions on that? So a lot of rules of algebra, as you can see in this class. Because our next function we have is y equals sine of x squared times e to the x. So our inner function is this x squared e to the x. Our outer function is sine. And so we're going to need to use the chain rule. And when we use that chain rule, when we take the derivative of the inside, notice we're going to have to use that product rule. So let's just first write it. So we have our outer function is sine. So when we look at y prime, we're going to find the second derivative, y double prime. So y prime, the derivative of our outer, derivative of sine is cosine of our inner, x squared times e to the x. And this is all times, I'm just going to write it, the derivative d dx of my inner function. So x squared e to the x. So let's take the derivative of the inner piece. So we have cosine of x squared e to the x. And we're using the product rule. So the derivative of my first function, x squared, that's 2x times e to the x plus my first function, x squared, times the derivative of e to the x. Well, derivative of e to the x is just e to the x. So notice that derivative of the inside, we have a x in common, and we have an e to the x in common that we can factor out. So we have cosine of our argument, x squared e to the x. We can pull out, what did I just say? We can pull out a single x and an e to the x. So if we pull out a single x from 2x e to the x, and we pull out e to the x, we're just left with 2. Plus, if we pull out an x from x squared, we're left with x, and we pulled out e to the x, so we don't have that left. Actually, oh my goodness. We have to find the, I would probably leave it like we had it. Because we have to find the second derivative, I don't want to have to apply the product rule a couple times in there. So let's just leave it. Later on, we can clean it up if we want to. If I was just asking to find the first derivative, I would probably do what I just did. But because I'm asked to find the second derivative, I don't want 3 products. Actually, there's even more than 3 products. So let's just leave it like this. So the second derivative, we got to look at the derivative of our first. So derivative of our outer. So derivative of cosine, it has a co, so it's negative sine of the inner, x squared e to the x times the derivative of the inner. We actually really just did that. Well, let me just write it. So d dx of x squared times e to the x. That is just my first function, the derivative of my first function. So I have that times my second function, which is 2x e to the x plus x squared e to the x. So that's just the first piece of the product rule, plus the first function. So our first function is just that cosine of x squared e to the x. Okay, so when we take the derivative, the second bracket over here, notice we're going to have to use the product rule. So derivative of the first, 2 to the x, that's a 2, times the second, e to the x. Plus, and this is just for this first term in here, the first function, 2 to the x, times the derivative of the second function, e to the x, which is just e to the x. Now let's take the derivative of the second piece in that second bracket. So x squared times e to the x, I got to use the product rule again. And so plus the derivative of x squared. Well, derivative of x squared is 2x times the second, e to the x, plus the first, x squared, times the derivative of the second, e to the x, which is e to the x. Okay, so I need to go back here because I still haven't taken the derivative of my inside function over here when I took the derivative of cosine x squared e to the x. So let's start to clean it up. So we have negative sine of x squared e to the x. This is all times this derivative, which we're going to have to use the product rule. So derivative of x squared is 2x times the second e to the x, plus the first x squared times the derivative of the second, which is e to the x. That all times 2x e to the x plus x squared e to the x. Plus cosine x squared e to the x. So it looks like I have some like terms in here. Maybe. I do. I have this x squared e to the x that doesn't have a like term. But we have this 2x e to the x plus 2x e to the x, that's plus 4x e to the x. And then plus 2 e to the x. I'm almost there. You could leave it like this, but just notice in here that this 2x e to the x plus x squared e to the x, I have another factor of that here, 2x e to the x times x squared e to the x. So really there's two of those. I could write that as 2x e to the x plus x squared e to the x quantity squared. And then I just would have that minus sine x, or minus sine, sorry, x squared e to the x. So not the prettiest thing, but we did it. So there was a lot going on there, a lot of different rules. I don't see anything in common that I could factor out of both of those groupings, so I would just leave it like that. So in front of you, you have a chart. You have some charts of the values of x, what f of x would be at those values of x, what g of x would be at those values of x, what the derivative of the values of x would be, and what the derivative of g of x of those values would be. And so find the derivatives with respect to x of the following combinations at the given value of x. So let's maybe jump to, how about D, f of x over g of x at x equals 2. So if I'm looking at, we want to find the derivative d dx, I haven't done it yet, of f of x divided by g of x at x equals 2. Well, let's first look at this. Where we're just taking the derivative of this function, f of x over g of x. We'll come back and look at x equals 2 in a second. So I know I need to apply the quotient rule. So this is f prime, the derivative of the numerator, f prime of x times the denominator, g of x, minus the numerator, f of x, times the derivative of the denominator, g prime of x, all over the denominator, g of x, quantity squared. So now if I wanted to evaluate this at x equals 2, I would just go in here, right? And I would plug in 2 wherever I see next. So I'm looking at f prime of 2 times g of 2 minus f of 2 times g prime of 2 all over g of 2 quantity squared. So I'm going to use my table now. F prime of 2, so my derivative function when x is 2 is 1/3. So I have 1/3 times g of 2. So g of 2, well, at x equals 2, g of 2 is 2, so times 2, minus f of 2. So f of 2 gives us 8 times g prime of 2. So g prime of 2 gives us -3 all over g of 2, which is 2 quantity squared. So 1/3 times 2 is 2/3. I have plus, because 2 negatives multiplying is positive, 24 all over 4. We don't like complex fractions. Let's just multiply by a fancy one, 3/3, and simplify it that way. And so if I distribute 3 to 2/3, you're just left with 2. 3 times 24 is 72, so plus 72, all over 4 times 3, which is 12. So we have 74 over 12. I notice 2 goes into at least both of those. 2 goes into 74 37 times. And 2 goes into 12 6 times. Or 6 and 1 6. So right there, that shows me you can know how to take the derivative of the quotient, the quotient rule, and then understand your function notation. So you should be able to do that with any of these types of problems, A through H. Okay, so let's also look at H. So I'm going to rewrite this. Let's rewrite it as y equals for H. So y equals, I know that taking the derivative of this, I'm going to have to use a couple different rules. And I don't know how to take the derivative of a square root, but I can take the derivative of something raised to the 1/2 power. So I'm going to rewrite this radical with a rational exponent. So this is the same thing as, and if this helps you to see this f squared of x, this is the same thing as f of x quantity squared. At g squared of x, this is g of x quantity squared. And this is all raised to the 1/2 power. So let's first look at the derivative of this. So I'm going to have to use my chain rule. And so my chain rule dy dx, I would bring down my exponent. This is my outer function. So 1/2 of my inner function. I'm just going to keep it how they had written it. Subtract 1 from our exponent. So 1/2 minus 1, 1/2 minus 2/2 is a -1/2. Times the derivative of the inside. So I'm going to have to, when I take the derivative of f of x quantity squared, I'm going to have to use the chain rule, bring my power down front, 2 of f of x times, because subtracting 1 from my exponent of 2 is 1, times the derivative of the inside, so f prime of x. Plus, so taking the derivative of this x, g of x squared, using the chain rule, bring down the 2 of g of x. Subtract 1 from my x power, exponent is just 1, times the derivative of the inside. And the inside was g of x, so g prime of x. So notice I can pull out a 2 inside that bracket. I have a 2 here and I have a 2 here. I could factor that out. And if I pull that 2 out, notice that when I multiply it to that 1/2, I just get 1. We want to evaluate this. It told us when x is 2. So really, we're going to look at f of 2 quantity squared plus g of 2 quantity squared. And that's all raised to the 1/2 power. Times, so now we're plugging into wherever we see an x, we pulled that 2 out. So we have f of 2 times f prime of 2 plus g of 2 times g prime of 2. So now we're going to use our chart. So f of 2 is 8. So we have 8 squared plus g of 2. G of 2 is 2. So 2 squared. All raised to the, and this should be a negative 1/2 power. Times f of 2, which is 8, times f prime of 2. F prime of 2 is 1/3. Plus g of 2. G of 2 is 2. Times g prime of 2, which is negative 3. So 8 squared is 64. 64 times 2 squared, which is 4. 64 plus 4 is 68. Raised to the negative 1/2 power. All times 8 times 1/3. So that's 8/3 minus 6. I want a common denominator. So negative 6 and our denominator would be 3. So that would be negative 18/3. I can bring that 68 down to the denominator and make that negative 1/2 power positive. And I have 8/3 minus 18/3 is negative 10/3. I don't like fractions within fractions. So this gives us negative 10 all over 3 square root of 68. Which has a perfect square in there that we can pull out. So 68, square root of 68 is the same thing as square root of 4 times 17. Square root of 4 is 2 root 17. So 2's cancel. 2 goes into negative 10 5 times, negative 5 times. So we have negative 5 in the numerator. All over 3 root 17. I'd be happy you got there, but technically we really don't like radicals in the denominator, so I could rationalize that denominator by multiplying both the top and the bottom by square root of 17. So this gives me negative 5 square roots of 17 all over, well, square root of 17 times square root of 17 is 17 times 3. That's 51. Okay. So we're given the table, we were using the table to find the derivative.